everyone, I'm Norman Wildberger. Today's famous mathematical problem goes back to the ancient Greeks. We're going to see how they computed the distances from the Earth to the Sun and the Moon. So along the way in this lecture, we'll summarize some basic facts about the solar system as it is known now. And we'll also have a look a little bit at the history of the ancient Greeks and some of the prominent mathematicians, astronomers, geographers that contributed to our understanding of the solar system. A good place to start is with a scale model of the solar system, or at least part of the solar system. This picture represents the plane of the planets, which is the plane of the board. And prominently here is the Sun, represented by this small red dot right there. Around the Sun you see the orbit of Mercury. Mercury is right here, but this dot here is actually out of scale, so that dot would be very much smaller if we were actually representing Mercury to scale. It would just be a speck of dust. And then a little bit further away, the orbit of Venus. And again, Venus would be a little bit bigger than Mercury, about 3 or 4 times the size, but still just a speck of dust in comparison to the Sun. A little bit further out, the Earth. And the Earth has, of course, a moon rotating around it. And I can represent both of those to scale by this little black dot here. So this little black dot represents, roughly, the size of the Earth together with the orbit of its moon around it. Okay, so that's how the Earth and the moon's orbit compares to the size of the Sun. Now if we're looking sort of down on this situation here, then the Mercury and Venus and the Earth, they're all rotating in this counterclockwise fashion, which is the same way that the Sun spins around or revolves. And most of the planets, in fact, revolve in the same way. Earth has a revolution that goes in this direction, so does Mercury. Venus is a little bit strange. It has a retrograde revolution that's going actually in the opposite direction. But most of the planets revolve like this, and all of the orbits are going in this counterclockwise direction, and they're almost all lying in this plane. The plane is usually called the ecliptic. Okay. So the study of the solar system is largely a two-dimensional geometry problem. Largely, but not entirely. Of course, there are the other planets around too, and they're off this picture. In terms of describing how far away they are, it's convenient to use the distance from the Sun to the Earth as some kind of convenient unit. That's called an astronomical unit. And it turns out to be about 150 million kilometers. A kilometer is a little bit less than a mile, so 1.61 kilometers makes a mile. So this would be slightly less, probably about 100 million miles. That's also 8 light minutes, so it takes a photon of light 8 minutes to make this journey. Light travels at the speed of 300,000 kilometers per second. And you can compute that in 8 minutes at this speed, you're roughly going to go this distance. So now in terms of this astronomical unit, this distance here, Mars, the orbit of Mars is a little bit further out. It's at 1.5 AU. Jupiter is the next one, the biggest planet. It's at 5.2 AU, so that would be 5 times this distance, another bigger circle around the Sun. Saturn's at 9.5, so we have to multiply this radius by 9.5. We get the radius of Saturn. Multiplied by almost 20, and we get the radius of Uranus. And multiplied by 30, we get the orbit of Neptune. These days, Pluto is not really considered a planet anymore. All right, so that's a rough scale orientation to our solar system, the way we understand it now. But, of course, in ancient times, this picture was far from being understood, and it's a big step to go from observing the night sky and watching what's happening with the stars and the moon and the planets and so on, to ultimately understanding things in this fashion. A huge intellectual achievement on the part of mankind, really, to have figured out that this is really what's happening up there. Okay, now let's zero in a little bit on the Earth and have a look at how it and the moon are positioned with respect to each other and their relative sizes. So again, this is an attempt at a realistic scale diagram. Here we have the Earth. The sun is in that direction over there, we'll suppose, and here is the moon. The moon goes around the Earth in this circular fashion, and it takes roughly a month or 28 days to do that. The moon is in different phases depending on its position with respect to the Earth and the sun. Right here, when the moon is on this side of its orbit, sort of on the opposite side as the sun is, then the light shining on the sun lights up always half of the moon, but that's the half that's visible to us. So if we're standing somewhere on the Earth and looking at the moon, we see a full moon. It's round, all of it's visible. However, if the moon is up here somewhere, then we will only see a half moon, and if the moon is on this side, in this direction of the sun, then we see a new moon or no light at all, essentially. Now it's important to realize also that the sun and the Earth are creating a shadow. So the Earth is blocking the rays of the sun. There's a shadow of the Earth, and that's rather a long shadow. And every so often the moon will pass through that shadow. That's a very important phenomenon called a lunar eclipse. There's another situation that happens when the moon passes in front of the Earth, in other words, between the Earth and the sun, and blocks the sun, or part of the sun. That's called a solar eclipse. All right, so there's some numbers that we'd like to keep in mind here. Some numbers that have been established now over the centuries with careful observation, and they are the following. First of all, the sun, which is the obviously dominant object in the solar system, its diameter is about 1,400,000 kilometers. The diameter of the Earth, on the other hand, is 12,700 kilometers. And the ratio between these things is roughly 100 to 1. If you multiply this by 100, then pretty well you get something like this, maybe a little bit more than 100. So the sun is about 100 times the size of the Earth in terms of its diameter. The diameter of the moon is roughly a third or a quarter of the diameter of the Earth. The distance from the sun to the Earth is, as we mentioned in the previous slide, 150 million kilometers. While the distance from the moon to the Earth, we now know, is 380,000 kilometers. Another interesting fact is that the angles subtended by the moon and the sun are roughly the same. They're both about 1/2 degree. So it's a rather remarkable coincidence that this small moon and this huge sun, the two main objects that we can see, are roughly the same size as we look at them. So in other words, the angle subtended by both of them is roughly equal, and that's about 1/2 degree. That has an important consequence, that this shadow actually meets here in an apex somewhere off the page, and this apex to here, this distance, is 108 times the diameter of the Earth. That's a consequence of it being 1/2 degree. So we know the length of the Earth's shadow by the angle subtended by the sun. So now we can go back to ancient times and ask this very interesting and popular question. How far away are the sun and the moon? How can we figure out, just by going outside in the night sky, looking up, observing the stars, making some measurements, perhaps over several months or maybe over several years. How can we figure out what's going on there? And in particular, how can we figure out how far away the moon and the sun are? This is not at all an easy problem. It gets a difficulty level of at least 5. It's of course a solved problem. And, but we'll see that it took the combination of quite a lot of thinkers working in different ways to come up with some reasonably decent estimates. And our main story concerns the ancient Greeks, who studied this kind of problem far more than anybody else did and far more successfully. And their understanding of astronomy is certainly one of the great achievements of that culture and one of the great gifts that they have passed on to subsequent cultures and generations. So we're going to talk a little bit about ancient Greek astronomy. Let's first of all admit that they were certainly influenced by earlier Babylonian and Egyptian astronomy. So the Babylonians had a well-established tradition of astronomy, as did the Egyptians. They made measurements, they had observatories, along with other ancient cultures. Almost all ancient cultures were interested in this general problem of what happens in the night sky. But in particular, the Babylonians and Egyptians, they influenced the early Greeks because a lot of the early Greeks would have gone traveling and would have visited Egypt or Mesopotamia and learnt from the scientists there. The first Greek astronomer was probably Thales, one of the founders of sort of the Greek way of thinking about mathematics, who lived from 624 to 547 BC roughly. And amongst other things, of course, famous for his contributions to geometry, but in astronomy he was known to have predicted a solar eclipse that happened on May 28th, 585 BC. He also believed that the Earth was a disk floating on water, so he did not have the spherical view of the Earth that happened later, that happened with the Pythagoreans that came after him. So Pythagoras, probably a student of Thales in some level, was from 570 to 495 BC, another very important figure. And he and his school adopted some different points of view. They really loved the idea of a sphere as being a beautiful, symmetrical object. And so they posited that the universe and the Earth were both spherical in shape. The idea is that the Earth is sitting here, and there's a larger sphere of fixed stars around the Earth. And that fixed star, sometimes called the celestial sphere or the heavenly sphere, on it, the stars themselves are there and they're moving around, but on that sphere also, or closely associated to it, are the sun, the moon, and the planets. At the time there were 5 planets that were clearly visible: Mercury, Venus, Mars, Jupiter, and Saturn. They hadn't seen Uranus and Neptune. You require telescopes for that. All right, so that was the setup of the Pythagoreans, who had a belief that the heavens and the earth all sort of moved in a spirit of harmony that was all governed by numbers. A little while later, Anaxagoras, who lived from 510 to 428 BC, was the first to propose an explanation for lunar eclipses in terms of the Earth's shadow. Now, when you look at a lunar eclipse and you see the shadow of the Earth passing over the moon, you see that the shadow is round or elliptical. And that's further evidence for the roundness of the Earth. But in fact, there was probably other evidence for the roundness of the Earth. This was probably also known from sailors. So when you're on a ship and you're sailing on a large body of open water like the Mediterranean, when you come to an island or something which, say, maybe has a mountain, you're going to see the top of that mountain before you see its base. In other words, you don't see the island just getting bigger and bigger in front of you. What you see is you see the top of the island first, and then you see more and more of the island from the top down, which is suggesting that we're actually on a sphere and the island is essentially moving over the horizon towards you. So sailors would have also probably inclined the mathematicians of the day to this general view that the Earth was round, in fact. So by the time of Plato, the great Athenian philosopher and writer and mathematical enthusiast, this was firmly enshrined in his doctrine, and he sort of summarized the Pythagorean view that there is basically the Earth in the middle of everything, and then that was a sphere, and then around the Earth there was this larger sphere, the heavenly sphere or celestial sphere, on which the stars sat, and this celestial sphere moved around. So it moved, spun on an axis, which also went through the center of the Earth, and that explains why the stars at night move around in a sort of circular fashion. Now, on that celestial sphere of fixed stars, there are also these 5 planets, as well as the sun and the moon. And Plato realized that these objects more or less lie on a plane which is not really at the same level as the equator of this sphere. It's inclined noticeably. And so there were these various objects, sun, moon, 5 planets, that were more or less making circular motions in this plane part of the heavenly sphere. But he also thought of these objects as being somewhat separate, maybe not exactly attached to the sphere. Some of them were closer to us than others. And the order of the distances from the Earth were the moon, that was the closest object, and then the sun, and then Venus, then Mercury, Mars, Jupiter, and Saturn. So that was Plato's view or summary of the Pythagorean view of astronomy at that time. That was 424 to 347 BC. I might also add, Plato, of course, very famous philosopher. He also spent some time in Syracuse, which is the hometown of Archimedes. And so he's another famous resident of Syracuse in Sicily. One of the greatest mathematicians of the ancient Greek world was Eudoxus, who lived from 408 to 355 BC. He also had something to do with astronomy, and he described the motions of the moon, sun, and planets by a rather complicated and ingenious system of interlocked spheres. So he posited that the motion of these things could be explained by thinking of them as being on a sphere. So, for example, here might be the sun. Okay? And the sun, he says, is rotating on an equator of a sphere which is moving around. Now, the axis of this sphere are themselves located on a larger sphere. And those axes themselves are spinning around. So there's another axis of this bigger sphere which is moving the entire configuration of the inner sphere around in a circular fashion. And then there's another bigger sphere on which these 2 axes points are fixed, which is also spinning. So we have one sphere inside another sphere inside another sphere. And the combined motions of these circular motions of each sphere explain, or pretty well explain, the motion of these objects, moon, sun, and planets, as understood at that time. So it was a very sophisticated mathematical construction. It was also rather abstract in the sense that he didn't, of course, claim that there were actual physical spheres. Just the idea that there's an abstract mathematical explanation of things that's somehow independent of the physical world, but explaining it. And then our key probably hero in this story today is Aristarchus, who is really the first very important astronomer in the Greek world, who really set out a lot of fundamental things in this book of his called On the Sizes and Distances of the Sun and the Moon. So he attempted to resolve this question of how big are the Sun and the Moon and how far away are they. He's also famous for having proposed a heliocentric theory of the solar system. He was the first person to suggest that maybe everything did not go around the Earth, and maybe in fact everything actually went around the Sun. Of course, many centuries later, 2,000 years after that, Copernicus came along and basically reintroduced this theory, along with a lot more evidence for it. All right, so Aristarchus made some computations, and they are computations which we can appreciate now, and they're somewhat ingenious and interesting, and what we're going to do is we're going to look at some of his computations. All right, so the first one has to do with this question of how to compare the distance from the Earth and the Moon to the distance from the Earth to the Sun. All right, so this is no longer a scale diagram. This is just a diagram that illustrates the geometry of it. The Moon is going around the Earth, and every so often the Moon is in a half-phase moon. That means we can see exactly half of it lit up. It's lit up exactly as a semicircle. All right. Now, Aristarchus argued, okay, well, that means that at that position, the Moon has to make a right angle between the line connecting the Earth and the line connecting to the Sun. That's going to be a right angle to ensure that when we're looking at the Moon from this direction, we see exactly half of it lit up. All right, so in other words, the Sun is exactly perpendicularly away from the Moon with regard to the line from us to the Moon. So that means there's a right triangle here. And Aristarchus realized that you could try to measure this angle here. So when the Moon was in this half full position, if you measured the angle between that line of sight to the Moon and the line of sight to the Sun, you get an angle there, then you could deduce the relative sizes of these two distances. So he made an estimate. It's a little bit hard to do this. You have to be a little bit careful. He said that maybe this is 87 degrees. Okay, it turns out that it's much closer to being 90 than that. It's actually 89 degrees and 52 seconds. So this is not at all a very good observational result. And that meant that this ratio that he got was in fact quite off. But he at least argued that, okay, if this is 87 degrees, then a bit of geometry. This was essentially before the days of trigonometry having been developed. But a little bit of geometry, then he can figure out that the ratio of this distance to the Sun and to this distance to the Moon is somewhere in the range between 18 and 20. Okay, in fact, the Sun is in fact much further away. This is actually much closer to being a right angle, which means that the Sun has to be further away. It's actually, this ratio has the value close to 346. Okay, but nevertheless, this argument showed that the Sun was much further away than the Moon. It's still roughly 20 times as far away as the Moon is, which means that the Sun is a lot bigger than the Moon, because they appear to us almost the same size. That means that the Sun is actually quite a major object, and that's probably what motivated him to say, well, if the Sun is so big, maybe it's playing the fundamental role. Maybe everything is going around it rather than everything around the Earth. So that was a very important calculation, even though, in fact, it wasn't very accurate. The next important player in our story is Eratosthenes, who lived from 284 to 192 BC. He was an Alexandrian. He lived in Alexandria. And at that time, Alexandria was the center of learning in the ancient world. So a lot of prominent mathematicians and scientists lived there. He was not just a mathematician, he was also a librarian, a geographer, and a surveyor. When I say a librarian, he was a librarian par excellence. He was the director of the great library at Alexandria, which was the greatest repository of books in the ancient world. So he made some important calculations because he was rather interested in the Earth and the geography of the Earth. He was perhaps the first real geographer. And to understand his calculation, we have to just understand a little bit about the tilting of the Earth. So here's the sun again, and here's the Earth diagrammatically going around the sun. It takes 1 year to go around. And I suppose we all know that the Earth is actually tilted with respect to this ecliptic plane in which its orbit lies. So there's actually quite a significant angle, it's roughly about 23 or 24 degrees, that the Earth makes with the vertical. And as it goes around or revolves around the sun, it's also rotating about its axis, and that axis stays parallel, so it's always facing the same direction of that axis. So that's the origin of our seasons. So if you're in the northern hemisphere, like in Europe, in Greece, or North America, or northern Asia, then when the Earth is tilted in this fashion, you're going to have summer, and when it's tilted in this fashion, you're going to have winter. And here are going to be spring and fall. And of course, if you're in the southern hemisphere, like Australia, it's reversed. All right, so this position of sort of maximum tilting is called the summer solstice in the northern hemisphere, and this was the winter solstice, and these other positions are called the equinoxes. So now we come to an important calculation of Eratosthenes, which he was able to make because he lived in this part of the world. Here is Alexandria. This is a little map of Egypt, Mediterranean up here. Here's the Nile River flowing north into the Mediterranean. And here, somewhere further down the Nile, is a town called Syene. Now this is actually the present-day place called Aswan. The Aswan Dam is just starting there. There's a big dam there nowadays. Of course, there wasn't back then. Now, Syene has the property that it's actually lying on the Tropic of Cancer. And what that means is that at the summer solstice, at this time of year, if we look at the Earth a little bit closer perspective there, the Earth is tilted. This is sort of the maximum tilt of the Earth towards the sun. And at that time of year, this Syene, which is right here on the northern hemisphere, is exactly in the line between the center of the Earth and the sun. That means the sun's rays are coming directly, perpendicularly down on it. Now, Eratosthenes knew this because there was a well in Syene, a deep well, that people had observed that on this one day of the year, in the summer solstice, the sun at noon shone right down this deep well, right to the bottom. It's a very unusual situation. The sun is So it's a very unusual situation that the sun is going right down this deep well. That means that Eratosthenes knew that the diagram was something like this. Now Alexandria, which is further north, is some other place on the sphere. It's almost directly north of Syene. And what Eratosthenes could measure is the angle between the sun's rays and the vertical where he was. So at noon of the same day, he measured the angle between the sun and the vertical. The vertical is easily obtained. You just drop a line with a weight on it. That's vertical. And then you measure how far from that vertical is the sun's rays coming in. And you see it's 7.2 degrees. Now, because the sun is very far away, he knew that this line coming into Alexandria and this line coming into Syene are more or less parallel. And so that this angle 7.2 here is the same as the angle subtended at the center of the Earth by this chord, this circular chord between Syene and Alexandria. So if you know this angle here, and you happen to know the distance between Alexandria and Syene, then it's easy to calculate the circumference of the Earth. And he knew that the distance between Alexandria and Syene was roughly 5,000 stadia. How did he know that? Well, what's a stadia, first of all? That's a Greek way of measuring things. In fact, there were two different kinds of stadia in operation. There was also an Egyptian stadia. It's roughly about 150 meters, or maybe roughly 500 feet, something like this. And he knew that the distance between Alexandria and Syene was roughly 5,000 stadia. He knew that because he was involved in surveying. He had done a lot of surveying for the Egyptian pharaoh. And he also knew that merchants who traveled between Alexandria and Syene typically took 50 days with their camels. And the camels traveled 100 stadia a day, and so he could deduce that 5,000 stadia was the distance between here and here. So knowing the angle is 7.2, knowing that this distance here along the surface of the Earth was 5,000 stadia, he made an easy calculation. The circumference of the Earth has to be 250,000 stadia, which is roughly about 25,000 miles, or close to 40,000 kilometers. And that was actually a very good calculation. That's within 2% of the true value. That's a very important calculation. The first time someone had figured out how big the Earth is. All right, so now let's return to Aristarchus and the question of how far away is the moon. So one natural way of trying to figure this out is to use a sort of triangulation or parallax argument, to take two observations at different points on the Earth's surface, take angles to the moon, and then compare a triangle. The trouble with that is that, first of all, the Earth is rotating, so you need to organize that the observation takes place at exactly the same time. And then secondly, there's this question of distances. It's not so easy to measure distances between two far separated points on the Earth's surface. So there's a question of measuring distances and also timekeeping that makes that actually practically a rather difficult way of trying to determine the distance to the moon. Aristarchus thought up another way of making this computation by using what we know about what happens in an eclipse, a lunar eclipse. So lunar eclipses were fascinating events, and they were much studied in the ancient world. People knew quite a lot about them and had observed them very carefully. So let me remind you that here is the Earth. It's a bigger diagram here. There's the Earth there. The sun is in that direction quite a long ways. And here is the shadow of the Earth. This is not to scale anymore. And this here represents the moon. The moon is going around the Earth in this circle. And this is the situation that we have when we have a lunar eclipse. The moon is coming along here. There's its orbit. And at some point it passes into the shadow of the Earth. That only happens in a full moon situation where the moon is essentially on the opposite side of the Earth as the sun is. So it moves into the shadow, and at some point you see part of the shadow of the Earth covering part of the moon. So you see this elliptical shadow or circular shadow of the Earth on the moon. And then as the moon moves, it moves into complete shadow, stays there maybe for a couple of hours, until it then emerges slowly on the other side. What's important in this diagram is that we know what this angle is. This angle, which is a half a degree roughly, is the same angle as subtended by the sun at the Earth's surface. Compared to the distance to the sun, the difference between here and here is not very much. All right, so if you look at the sun and ask, well, what is that angle? That's something that you can do, although please don't look at the sun directly. If you hold out a quarter or a dime or something like that, you have to hold it out quite a ways before it appears the same size to your eye as does the sun or the moon. This is much easier to do with a full moon, okay, much safer. And you can try it, and you realize that this angle is such that the ratio between this diameter and this distance here is 1 to 108. That's the measure of the angle that's subtended by either the moon or the sun. They're pretty well the same. And you can see that if this is the shadow of the sun, then at this point here, if you were able to look here, the angle subtended by the Earth would be exactly the same as the angle subtended by the sun. That's what it means. All right, so we know this angle, and so we know the ratio between this diameter of the Earth and this distance here. The other critical thing that we need to observe is what happens in the eclipse. If you watch the eclipse carefully, you can deduce that this distance here is exactly 2.5 times this distance by watching how long it takes to pass through the shadow. So those are the two observations that are important in terms of this diagram, along with the fact that the angle subtended is a ½ degree. And that has not just this angle here as an application, but also crucially this angle here. Right? So if you're on the Earth and you're looking at the moon, then the angle subtended by you is again a ½ degree. Because the sun and the moon subtend the same angle roughly. They are the same size. Alright, so that means that in this little figure we have two similar triangles. Actually we have three similar triangles. The triangle FAD, here, 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 that isosceles triangle, is similar to the triangle DCE. DCE, that's another isosceles triangle with the same angle, which is similar to the triangle BAC. But what we know is that this side of this triangle is 2.5 times this side of this triangle. That is 2.5 times this. Well, that means that this must be 2.5 times this. So AC then must be 3.5 times DC. AC is 3.5 times DC. And correspondingly, BC is 3.5 times DE. So comparing this big isosceles triangle with this little isosceles triangle, the ratios of this side to this side are 3.5 to 1. So the ratio of this to this must be 3.5 to 1. That means that the Earth is 3.5 times the diameter of the moon. And since we know that this entire distance is 108 times the diameter of the Earth, we can deduce that this distance from the Earth to the moon is 108 times the diameter of the moon. So we've established, Aristarchus established the following conclusion, that the diameter of the moon is between 1/3 and 1/4 of the diameter of the Earth, and that the distance to the moon is 108 times its diameter. So if we go back to this diagram here with these figures on it, we can summarize that the ancient Greeks knew the following. They knew, thanks to Eratosthenes' calculation with the well at Syene, they knew that the diameter of the Earth was pretty well 12,700 kilometers. They were pretty close, within a few percent of that. They knew that the diameter of the moon was 3,500 kilometers, within a few percent of that. They knew that the distance from the moon to the Earth was 380,000 kilometers. Pretty close. In terms of the distance from the sun to the Earth, we now know that's 150 million miles. Aristarchus' original calculations were much short of that, but his calculations were improved by later astronomers and geometers, so that the ancient Greeks got reasonably close, within maybe a factor of 2 or 3 to that at some point. All right, so it's quite a lovely achievement, and sort of setting up our system today. Of course, there was still much more to be done. There's still many more questions to be answered here. There's still the question of how the planets move, which is a very, very important problem that we'll talk about later. And that leads to the Europeans' important contribution to the picture of astronomy that we have now today. In our next lecture on famous math problems, we're going to talk about probably the most important formula in calculus, which is the integral of x to the n. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.